Now we're going to talk about significant numbers. This is when we're talking about how accurate and precise the measurements are in the lab and the data that we're collecting. So accuracy is how close it is to the real value, while precision is how close all the trials are together. So here in my bullseye, the accuracy would be hitting the center of the bullseye. Precision would be the clumping of the darts together. So if we look, see if you can figure out which one is accurate and which one is precise. So in the first picture, we're both accurate and precise because we're clumped on the bullseye. The second picture, we're precise because we're clumped together, but not accurate because we didn't hit the bullseye. In the third picture, we're not accurate or precise because we're all over the place. And same with the last picture. This one you could argue that it might be a little accurate because you are closer to the bullseye. We can show our accuracy by finding the percent error. The formula for percent error is accepted minus experimental divided by accepted times 100. Please make sure that you have that written down. I would highlight it in your notes. It is one of the very few that are not given to you in your reference tables. So in our example, a student calculates a substance density to be 1.4 grams per milliliter. Because the student calculated it, that is the experimental. Anytime it is student determined or you measure it in the lab, that's experimental. The correct value, 1.36 grams per milliliter, is the accepted value. So accepted or correct or true, those all mean the same thing. And then we're looking for the percent error. So we're simply going to plug this in, or these values into our formula. So we have our accepted minus our theoretical divided by our accepted times 100. The lines that are going there are your absolute value signs, meaning you cannot have a negative percent. You should never have a negative percent. You will always take the absolute value of that. So when you subtract, then divide and multiply, you get an answer of 2.94% error. That's pretty good. The larger that value is, that means the less accurate you are. So you want a small percent error. Significant figures are anything that we know for certain plus an estimated position. Things that are non-zero are significant. So when we look at this value for the pencil, 18.73, all of those are significant figures. The 3 is the estimate that we're making from the ruler. Zeros can be significant if they're between non-zero digits, if they're at the end of the number and to the right of the decimal, or if they're at the end of the number, or at the end of the number and left of the decimal with an actual digit. Let's go over some examples. So 28.6. The very first rule for significant figures is that anything that's not zero is significant. So all 3 of those would count because they're all non-zero digits. So this has 3 significant figures. I abbreviate that Sig Fig. In our next number, we have 3, 4, 4, which are non-zero digits, so they will count. The 0 then we have to think about. It's at the end of the number and to the left of a decimal. Therefore, it counts. So there's 4 significant figures in that number. Next we have 910. So the 9 and 1 count because they're not zero. This time the 0 is non-significant because there's no decimal. So zeros at the end of a number can only count if you see a decimal. Here's a larger number. We know the 2 and the 3 would count because they're non-zero digits. All of those zeros are in between the 2 and the 3, so they're sandwiched between the 2 and the 3. Therefore, they all count. So all of those numbers are significant because the zeros are being sandwiched. One more number to look at. We know the 6 and the 7 are significant because they're non-zero. Zeros that come after those could count. Zeros that come before the 6 can never count. So those 3 zeros that are listed in the front there are just placeholders. They're not significant. The zeros after the 7 do count because there is a decimal. So that has 4 significant figures. When we're reading lab equipment, we would want to give all numbers we know for sure. So we know it's definitely past the 30. This is 35, so this would be 36. So we know it's going to be, that should be a 6, sorry, a 36. And then we're going to estimate that last digit. So we would say 36.5 milliliters. Again, that should be a 6. I'm sorry about that. If we were to look at this ruler, we know that it's at the 5. We're going to say it's exactly at the 5, so we're estimating the 0. So that's significant. We have to include it because all numbers known for sure plus 1 estimate, and we're estimating that it's exactly 5, so we have to put a 0. Math and Sig Figs. So most of the time, we're not just writing down a single number. We're collecting those numbers, and then we're going to analyze them by doing some math to them in our labs. So when we add and subtract, we go based on the fewest decimal places. So in this problem here, we have 5.44, which has 2 decimal places. The next number has 4 decimal places. So which is fewer, 2 or 4? So we want to make sure that our answer is rounded to 2 decimal places. So our final answer is 2.83 meters. Hopefully you're typing this into your calculator as we're going so that you can see how it goes from what's in the calculator to what our final answer is. Let's try another one. We're adding. Anytime you add or subtract, it is based on decimal places. The first number has 3 decimal places. The second number has 5 decimal places. So which is fewer, 5 or 3? So we would want 3 decimal places. So our answer then is 10.156. It doesn't matter how many numbers come before. We're just worried about decimal places when we add and subtract. Now when we multiply and divide, we have to look at the whole number, not just the decimal places. So when we multiply or divide, we're looking for the fewest significant figures total. So here we have 2.4 times 15.02. Well, 2.4 has 2 significant figures. They're both non-zero. 15.02 has 4 significant figures, 1, 5, and 2. The 0 is sandwiched, so it counts. So which is less, 2 or 4? 2. So we want our answer to have 2 significant figures. So we get 36. Again, make sure you type it into the calculator to see what it should have been or what it is in the calculator versus what we're writing down. Then we have to look at our units. Grams over milliliters times milliliters. So the milliliters would cancel, leaving us with grams. One more problem. 0.0179 divided by 4.130. So this top number here has the 1, the 7, and the 9. Those all count. The zeros are in front of the 1, so they are not significant. So this number has 3 significant figures. The number on the bottom has the 4, the 1, and the 3. The 0 comes at the end, and we have a decimal. So the 0 counts this time, and we have 4 significant figures. So which is less, 3 or 4? 3. So our answer needs to have 3 significant figures. So we type it into the calculator, and then we're going to write down the first 3 significant figures, making sure to round that last one. The zeros here don't count. We have to write them because they're placeholders, but they're not considered significant, which is why we didn't stop at the 4. Instead, we went 4, 3, 3. Those are non-zero digits, so those are our 3 significant figures. For the unit, we're doing grams divided by centimeters cubed. None of that's the same, so none of it cancels out, and our units would be grams per centimeters cubed.